Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. For millennia, the human body remained medicine's greatest mystery. Physicians could observe symptoms, feel for abnormalities, and listen to internal sounds, but the living interior of their patients remained as hidden as the far side of the moon. When illness struck deep within organs or tissues, doctors could only guess at the underlying cause. Surgery meant cutting blindly into darkness, hoping experience and intuition would guide their hands to the source of disease. The challenge was fundamental. How do you see inside something without destroying it? Light cannot penetrate flesh beyond the surface. Traditional X-rays, discovered by Wilhelm Röntgen in 1895, offered the first glimpse through skin and muscle, but they revealed only bones and dense tissues. Soft organs, the brain, heart, liver, kidneys, remained invisible shadows on radiographic film. This limitation had profound consequences. Brain tumors grew undetected until they caused devastating symptoms. Heart disease progressed silently, until catastrophic failure. Cancers spread through soft tissues, invisible to the diagnostic tools of the time. Medicine was practiced in a world of educated guesswork, where the most critical information lay forever beyond reach. By the mid-20th century, medical imaging had advanced incrementally. Contrast agents could highlight blood vessels and organs on X-ray films. Computed tomography, developed in the 1970s, used multiple X-ray beams to create cross-sectional images of the body. But these techniques still relied on radiation, limiting their use, and soft tissue contrast remained poor. The dream of medicine was to develop a window into the living body, one that could reveal the intricate details of soft tissues without causing harm. This vision seemed almost impossibly ambitious. How could science peer through flesh and bone to see the delicate structures within? The answer would come from an unexpected source: the quantum properties of atomic nuclei and the pioneering work of physicists who dared to imagine the impossible. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The story of magnetic resonance imaging begins not in hospitals or medical schools, but in physics laboratories where scientists were investigating the fundamental properties of matter itself. In 1946, two teams of physicists, Felix Bloch at Stanford University and Edward Purcell at Harvard University, independently discovered that atomic nuclei could absorb and emit electromagnetic radiation when placed in strong magnetic fields. This phenomenon, called nuclear magnetic resonance, or NMR, would eventually revolutionize our understanding of molecular structure. The principle underlying NMR is elegantly simple yet profound. Certain atomic nuclei, particularly hydrogen nuclei found abundantly in water and fat, behave like tiny magnets. When placed in a powerful magnetic field, these nuclear magnets align themselves with the field. A brief pulse of radio waves can then flip these nuclei into higher energy states. As they return to their original alignment, they emit radio signals that can be detected and analyzed. Initially, NMR was purely a tool for chemists and physicists studying molecular structure. The technique could reveal precise information about chemical bonds and molecular environments, but the human body is approximately 60% water, with hydrogen nuclei present in virtually every tissue. Could this quantum phenomenon somehow be harnessed to create images of living tissue? The possibility seemed remote, requiring technological leaps that existed only in the realm of speculation. Yet, within 3 decades, this quantum effect would transform medicine forever, opening an unprecedented window into the living human body. The quantum world operates by rules that defy everyday intuition, yet these strange principles would become the foundation for one of medicine's greatest diagnostic tools. To understand how magnetic resonance imaging emerged from nuclear physics, we must first explore the peculiar behavior of atomic nuclei when subjected to powerful magnetic fields. At the heart of nuclear magnetic resonance lies a quantum property called spin. Protons and neutrons, the particles that make up atomic nuclei, possess an intrinsic angular momentum that causes them to behave like microscopic spinning tops. This spin gives certain nuclei, particularly hydrogen nuclei, which are simply single protons, a magnetic moment making them act like tiny bar magnets. In the absence of external magnetic fields, these nuclear magnets point in random directions. But when placed in a strong, uniform magnetic field, something remarkable happens. The nuclear magnets align themselves either parallel or anti-parallel to the field, creating two distinct energy states. The parallel alignment represents the lower energy state, while the anti-parallel alignment represents the higher energy state. Felix Bloch and Edward Purcell, working independently in 1946, discovered that these aligned nuclei could absorb electromagnetic radiation at a specific frequency, causing them to flip from the lower energy state to the higher energy state. This resonance frequency depends on the strength of the magnetic field and the type of nucleus involved. For hydrogen nuclei at typical magnetic field strengths, this frequency falls in the radio wave portion of the electromagnetic spectrum. The breakthrough came when Bloch and Purcell realized that the nuclei would eventually return to their lower energy state, releasing the absorbed energy as radio waves. By detecting these emitted radio signals, scientists could identify the presence and quantity of specific types of nuclei in a sample. More importantly, the exact frequency and intensity of these signals provided detailed information about the chemical environment surrounding each nucleus. This environmental sensitivity proved crucial for the future development of medical imaging. Hydrogen nuclei in different tissues, muscle, fat, brain matter, blood, experience slightly different local magnetic environments due to variations in chemical composition and molecular structure. These differences, though minute, create distinct NMR signatures for different tissue types. In the 1950s and 60s, NMR spectroscopy became an indispensable tool for chemists and biochemists. Researchers could determine molecular structures by analyzing the pattern of radio signals emitted by different nuclei within a compound. The technique revealed information impossible to obtain through any other method, providing unprecedented insight into the three-dimensional arrangement of atoms within molecules. However, early NMR experiments required hours or even days to collect sufficient data for analysis. The signals were often weak, and the technology for signal detection and processing was primitive by modern standards. The idea of using NMR to create real-time images of living tissue seemed impossibly ambitious. The quantum mechanical principles underlying NMR also introduced another crucial concept: relaxation times. After being excited by radio waves, nuclei return to their equilibrium state through two distinct processes. T1 relaxation, also called longitudinal relaxation, describes how quickly the nuclei realign with the external magnetic field. T2 relaxation, or transverse relaxation, describes how quickly the nuclei lose phase coherence with each other. These relaxation times vary significantly between different tissues, providing another layer of contrast for potential imaging applications. Brain tissue, muscle, fat, and pathological tissues like tumors all exhibit characteristic relaxation times. This discovery suggested that NMR could potentially differentiate between healthy and diseased tissues, a capability that would prove revolutionary for medical diagnosis. By the late 1960s, the stage was set for a conceptual leap that would transform NMR from a laboratory curiosity into a medical imaging modality. The quantum foundation was solid, the physics well understood, but translating these principles into practical medical technology would require visionary thinking and extraordinary technical innovation. In 1971, a chemistry professor at the State University of New York at Stony Brook was analyzing NMR data when he conceived an idea that would revolutionize medicine. Paul Lauterbur, studying the molecular structure of compounds, using nuclear magnetic resonance spectroscopy, realized that the same principles could potentially create images of objects, including living tissue. The conceptual breakthrough was elegantly simple yet profound. Traditional NMR spectroscopy used uniform magnetic fields to analyze the overall composition of samples, but Lauterbur envisioned deliberately creating non-uniform magnetic fields, magnetic field gradients, that would allow spatial localization of NMR signals. By varying the magnetic field strength across different regions of space, each location would have its own unique resonance frequency, creating a spatial signature that could be decoded into an image. Lauterbur's initial experiments were conducted on simple objects, test tubes filled with water. By applying magnetic field gradients in different directions and collecting NMR signals, he could reconstruct two-dimensional images showing the cross-sectional structure of his samples. The first published image, appearing in the journal Nature in 1973, showed the cross-section of two thin tubes of water, a humble beginning for what would become one of medicine's most powerful diagnostic tools. The technical challenges were immense. Creating precise, controlled magnetic field gradients required sophisticated engineering. The mathematical techniques for reconstructing images from NMR data had to be developed from scratch. Signal processing capabilities were limited by the computing technology of the early 1970s. Yet Lauterbur's vision drove rapid innovation across multiple disciplines. Simultaneously, other researchers were exploring similar concepts. Raymond Damadian, a physician and researcher at the State University of New York Downstate Medical Center, had discovered that NMR relaxation times differed significantly between normal and cancerous tissues. In 1971, he published groundbreaking research showing that malignant tumors could be distinguished from healthy tissue based on their unique NMR signatures. Damadian envisioned using NMR to detect cancer throughout the human body, calling his concept a tumor detector. His approach initially focused on analyzing bulk tissue samples rather than creating detailed images, but his work demonstrated the medical potential of nuclear magnetic resonance techniques. Meanwhile, in England, Peter Mansfield at the University of Nottingham was developing mathematical methods for rapidly acquiring and processing NMR data. Mansfield's innovations in pulse sequences and signal acquisition would prove crucial for making NMR imaging practical for clinical use. His work focused on developing faster imaging techniques that could capture physiological processes in real time. The convergence of these research streams created the foundation for magnetic resonance imaging. Lauterbur's spatial encoding concept, Damadian's medical vision, and Mansfield's mathematical innovations combined to transform NMR from a laboratory technique into a potential medical imaging modality. Early images were crude by modern standards. Resolution was poor, acquisition times were measured in hours, and only the largest anatomical structures were visible. The first attempts to image living tissue were conducted on excised specimens, removed organs and tissue samples that could be studied without the complexities of living physiology. The transition from spectroscopy to imaging required fundamental rethinking of experimental design. Spectroscopists were accustomed to obtaining detailed chemical information from small, homogeneous samples. Imaging demanded rapid data acquisition from large, heterogeneous objects while maintaining sufficient spatial resolution to reveal anatomical details. Signal-to-noise ratio became a critical limitation. Living tissue produces relatively weak NMR signals, and the process of spatial encoding further reduces signal strength. Early imaging systems required powerful magnets, sensitive radio frequency detection equipment, and sophisticated signal processing capabilities that pushed the boundaries of available technology. Despite these challenges, the potential applications were immediately apparent. Unlike X-rays, NMR imaging could differentiate between soft tissues with similar densities. Unlike invasive procedures, it caused no apparent biological damage. The technique could potentially reveal pathological changes before they became visible through other diagnostic methods. The visionary leap from nuclear physics to medical imaging was complete, setting the stage for the engineering revolution that would make MRI a clinical reality. Transforming the theoretical concept of nuclear magnetic resonance imaging into a functioning medical device, required solving engineering challenges that seemed impossible with 1970s technology. The task demanded unprecedented magnetic field stability, radio frequency precision, and computational power, all integrated into a machine that could safely accommodate human patients. The magnetic field requirements alone presented extraordinary challenges. Effective NMR imaging required magnetic fields thousands of times stronger than Earth's natural magnetic field, maintained with incredible uniformity across the entire imaging volume. Field variations of more than a few parts per million would destroy image quality, yet the magnetic field had to encompass regions large enough to accommodate human patients. Early researchers explored various approaches to generating these powerful, uniform fields. Permanent magnets were considered, but proved impractical due to their enormous weight and limited field strength. Conventional electromagnets required massive amounts of electrical power and generated significant heat. The solution, ultimately, came from superconducting magnets, coils of wire that, when cooled to near absolute zero, could carry electrical current without resistance. Superconducting magnet technology in the 1970s was exotic and expensive. The superconducting wires were brittle and difficult to manufacture. Cooling systems required liquid helium at temperatures approaching -269 degrees Celsius. Magnetic field quenches, sudden losses of superconductivity that could destroy the magnet, were constant threats. Yet only superconducting systems could provide the field strength and stability required for high-quality imaging. Raymond Damadian's team at SUNY Downstate built one of the first human-scale chemistry imaging systems dubbed Indomitable. The machine used a resistive electromagnet weighing several tons, consuming enormous amounts of electrical power and requiring extensive cooling systems. Despite these limitations, Indomitable produced the first NMR images of living human beings in 1977. The first human images were revelatory despite their crude appearance. Cross-sections through the chest revealed the heart, lungs, and major blood vessels. Brain images showed the basic structure of cerebral hemispheres, ventricles, and brainstem. Most importantly, different tissues exhibited distinct signal intensities, confirming that NMR imaging could differentiate between various types of soft tissue. However, image acquisition required several hours, during which patients had to remain absolutely motionless. The slightest movement would blur the images beyond recognition. Breathing, heartbeat, and involuntary muscle contractions all degraded image quality. The challenge of imaging living, moving subjects demanded innovative solutions. Parallel developments in computer technology proved crucial for MRI development. The mathematical reconstruction of images from NMR data required complex calculations involving Fourier, transforms, and matrix operations. Early imaging systems relied on mini-computers that were primitive by modern standards, but represented cutting-edge technology in the 1970s. Signal processing posed another layer of complexity. NMR signals from human tissue are extremely weak, millions of times weaker than typical radio broadcasts. Detecting these faint signals required sophisticated radio frequency electronics, specialized amplifiers, and careful shielding from electromagnetic interference. Hospitals, with their abundance of electrical equipment, proved particularly challenging. Environments for sensitive NMR detection systems. Safety concerns added another dimension to the engineering challenges. The powerful magnetic fields required for imaging could affect pacemakers, metal implants, and ferromagnetic objects. Liquid helium cooling systems presented risks of asphyxiation if improperly ventilated. Radio frequency heating of tissue had to be carefully controlled to prevent burns. Commercial development of MRI systems began in the late 1970s as several companies recognized the technology's medical potential. General Electric, Siemens, and other major corporations invested heavily in MRI research and development. The race to produce reliable, clinically viable systems drove rapid innovation in magnet design, electronics, and software. The first commercial MRI systems appeared in the early 1980s, representing the culmination of a decade of intensive engineering development. These machines were enormous, expensive, and required specialized facilities with magnetic shielding and helium handling capabilities. Yet they produced images of unprecedented clarity, revealing anatomical details invisible to any other imaging. Technique. The engineering achievement was remarkable. Teams of physicists, engineers, and computer scientists had successfully translated quantum mechanical principles into practical medical technology. The impossible had become routine, opening an entirely new chapter in medical diagnosis and treatment. On July 3, 1977, medical history was made in a laboratory at the State University of New York Downstate Medical Center. Raymond Damadian and his colleagues Lawrence Minkoff and Michael Goldsmith completed the first magnetic resonance image of a living human being. The subject was Minkoff himself, who lay motionless inside the indomitable scanner for nearly 5 hours as the machine slowly assembled an image of his chest. The resulting image was crude by modern standards, a grainy, low-resolution cross-section that revealed basic anatomical structures in shades of gray. Yet for the first time in human history, physicians could peer inside a living person without surgery, radiation, or invasive procedures. The heart appeared as a dark region surrounded by the brighter signals of lung tissue. Major blood vessels were visible as distinct structures. Most remarkably, different soft tissues exhibited clearly different signal intensities, proving that MRI could distinguish between organs that appeared identical on conventional X-rays. The medical implications were immediately apparent. Brain imaging revealed structures that had previously been accessible only through dangerous procedures like pneumoencephalography, which involved replacing cerebrospinal fluid with air to create contrast on X-ray images. MRI could visualize the brain's gray and white matter, the ventricles filled with cerebrospinal fluid, and the major anatomical divisions, all without any risk to the patient. Early brain images astonished neurologists and neurosurgeons. The technology could detect brain tumors, strokes, and other pathological changes with unprecedented clarity. Multiple sclerosis, a disease that affects the brain's white matter, became clearly visible for the first time. Physicians could observe the characteristic lesions scattered throughout the brain and spinal cord, enabling earlier diagnosis and better monitoring of disease progression. Abdominal imaging presented new possibilities for diagnosing liver disease, kidney disorders, and abdominal cancers. The liver's complex internal structure became visible in ways impossible with conventional imaging. Kidney function could be assessed by observing how quickly contrast agents moved through the renal system. Pancreatic tumors, notoriously difficult to detect with other imaging methods, could be identified in their early stages. Cardiac imaging opened entirely new frontiers in cardiology. MRI could visualize the heart's chambers, valves, and major vessels without the need for cardiac catheterization. Heart muscle damaged by heart attacks appeared different from healthy tissue, allowing physicians to assess the extent of cardiac damage. Blood flow through coronary arteries could be observed and measured, providing crucial information for treatment planning. The technology's ability to image in any plane proved revolutionary. Unlike X-rays or early CT scanners, which were limited to specific orientations, MRI could create images in sagittal, coronal, transverse, or any arbitrary plane. This flexibility allowed physicians to examine anatomical structures from multiple perspectives, providing comprehensive three-dimensional understanding of pathological processes. Musculoskeletal imaging revealed the internal structure of joints, muscles, tendons, and ligaments with extraordinary detail. Sports medicine was revolutionized as physicians could diagnose torn ligaments, muscle injuries, and joint disorders without exploratory surgery. Spinal imaging could detect herniated discs, spinal cord compression, and other conditions that cause back pain and neurological symptoms. The absence of ionizing radiation was perhaps MRI's greatest advantage. Unlike X-rays, CT scans, or nuclear medicine procedures, magnetic resonance imaging posed no known biological risks. Patients could undergo multiple scans without cumulative radiation exposure. Pregnant women could be imaged without risk to the developing fetus. Children could receive comprehensive diagnostic workups without concerns about radiation-induced cancer. However, early clinical implementation faced significant challenges. Image acquisition times remained lengthy, often requiring 30 minutes to several hours for complete examinations. Patient comfort was poor inside the narrow, noisy scanner tubes. Claustrophobia affected many patients, limiting the technology's clinical utility. Motion artifacts from breathing, heartbeat, and involuntary movements continued to degrade image quality. Despite these limitations, the medical community quickly recognized MRI's transformative potential. Hospitals began planning for MRI installations, though the enormous cost and facility requirements limited initial adoption to major medical centers. Radiologists required extensive training to interpret the new type of images, which provided information unavailable through any other imaging technique. Research programs proliferated as investigators explored MRI's diagnostic capabilities across medical specialties. New imaging sequences were developed to enhance contrast between different tissue types. Contrast agents were introduced to highlight blood vessels and detect areas of abnormal tissue perfusion. The foundation was laid for MRI's evolution, from an experimental technique into an indispensable clinical tool. The first glimpse within the human body had opened a window that would never close, forever changing medical practice and patient care. The early 1980s marked a critical transition period for magnetic resonance imaging. While the first human images had proven the technology's medical potential, significant barriers prevented widespread clinical adoption. Scan times, measured in hours, were impractical for routine patient care. Image quality suffered from motion artifacts and limited resolution. The massive, expensive machines required specialized facilities and highly trained operators. Overcoming these obstacles would require systematic innovation across every aspect of MRI technology. Signal acquisition speed became the primary focus of improvement efforts. The original imaging methods collected data sequentially, building images one line at a time over extended periods. Peter Mansfield's research group at the University of Nottingham developed echoplanar imaging, a revolutionary technique that could acquire entire images in milliseconds rather than hours. This breakthrough made real-time imaging possible, allowing physicians to observe physiological processes as they occurred. Gradient system improvements enabled faster spatial encoding and better image resolution. Early MRI systems used weak, slowly switching magnetic field gradients that limited imaging speed and spatial precision. Advanced gradient coils, powered by high-performance amplifiers, could generate stronger fields that switched on and off thousands of times per second. These rapid gradient changes enabled faster data acquisition while maintaining or improving image quality. Pulse sequence development provided radiologists with tools to emphasize different tissue characteristics. Spin echo sequences highlighted anatomical structure. Gradient echo sequences enabled rapid imaging of blood flow and cardiac function. Inversion recovery sequences could suppress signals from specific tissue types, enhancing contrast between pathological and normal tissues. T1 weighted images emphasized anatomical detail, while T2 weighted images highlighted pathological changes like inflammation and tumors. Computer technology advances were crucial for MRI's clinical success. Image reconstruction algorithms became more sophisticated, reducing artifacts and improving image quality. Digital storage systems replaced film-based imaging, enabling rapid image retrieval and manipulation. Three-dimensional imaging capabilities allowed reconstruction of volumetric datasets from multiple two-dimensional slices. Patient comfort improvements addressed one of MRI's most significant limitations. Early scanners were narrow, claustrophobic tubes that caused anxiety and panic in many patients. Open MRI systems, with wider patient openings or completely open designs, reduced claustrophobia while maintaining acceptable image quality. Noise reduction technologies made the scanning experience more tolerable, as early MRI systems produced intense acoustic noise from rapidly switching gradient coils. Contrast agents expanded MRI's diagnostic capabilities. Gadolinium-based compounds injected intravenously highlighted areas of abnormal blood flow or tissue breakdown. These agents made brain tumors more conspicuous by revealing areas where the blood-brain barrier was compromised. Vascular imaging became possible, allowing non-invasive visualization of blood vessels throughout the body without traditional angiography. Safety protocols were established as MRI installations proliferated. The powerful magnetic fields posed unique hazards absent from other imaging modalities. Ferromagnetic objects could become dangerous projectiles if brought too close to the scanner. Patients with pacemakers, cochlear implants, or certain metallic implants required careful evaluation before imaging. Comprehensive screening procedures were developed to identify potential safety risks. Quality assurance programs ensured consistent image quality across different MRI systems and institutions. Standardized test objects, called phantoms, allowed technologists to monitor system performance daily. Image quality parameters like signal-to-noise ratio, spatial resolution, and contrast sensitivity were measured regularly to detect system degradation before it affected patient care. Training programs prepared healthcare professionals for MRI's clinical integration. Radiologists learned to interpret the new image contrast and anatomical appearances unique to magnetic resonance imaging. Technologists mastered the complex scanning protocols and safety procedures required for safe, effective MRI operations. Referring physicians learned to select appropriate patients and clinical indications for MRI examinations. Cost reduction efforts made MRI more accessible to healthcare institutions worldwide. Manufacturing improvements reduced magnet costs and simplified scanner installation requirements. Helium recycling systems minimized the ongoing expense of superconducting magnet operation. Standardized designs enabled mass production, reducing per-unit costs while maintaining quality and reliability. Clinical research established MRI's diagnostic accuracy across medical specialties. Comparative studies demonstrated superior soft tissue contrast compared to CT scanning for many applications. Specific clinical protocols were developed for common diagnostic problems like knee injuries, brain tumors, and cardiac disease. Evidence-based guidelines helped physicians determine when MRI was the most appropriate imaging choice. By the mid-1980s, these collective improvements had transformed MRI from an experimental technique into a practical clinical tool. Scan times dropped from hours to minutes. Image quality improved dramatically, while maintaining the technology's fundamental advantages of excellent soft tissue contrast and freedom from ionizing radiation. The stage was set for MRI's emergence as one of medicine's most valuable diagnostic technologies. By the 1990s, magnetic resonance imaging had achieved something unprecedented in medical history: the ability to peer inside the living human body with exquisite detail, distinguishing between soft tissues that were invisible to all previous imaging methods, and accomplishing this feat without causing any known biological harm. The technology that began as an abstract physics experiment had become medicine's most versatile diagnostic tool, fundamentally transforming healthcare across every medical specialty. The revolution's scope became apparent as MRI installations spread worldwide. Major medical centers acquired multiple scanners to meet growing clinical demand. Smaller hospitals invested in MRI systems as the technology became more affordable and user-friendly. By the early 2000s, tens of thousands of MRI systems were operating globally, performing millions of examinations annually and generating diagnostic information impossible to obtain through any other means. Neuroimaging emerged as MRI's most dramatic success story. The brain, previously accessible only through dangerous invasive procedures, became visible in unprecedented detail. Neurosurgeons could plan complex operations using three-dimensional MRI maps, showing the precise relationship between tumors and critical brain structures. Stroke patients received immediate diagnosis, enabling time-critical treatments that saved both lives and neurological function. Functional MRI, developed in the 1990s, opened entirely new research frontiers by visualizing brain activity in real time. Scientists could observe which brain regions activated during specific tasks, emotions, or thought processes. This technology revolutionized neuroscience research and began providing insights into conditions like depression, schizophrenia, and autism spectrum disorders. Cardiac MRI evolved into the gold standard for assessing heart function and structure. Physicians could measure cardiac output, evaluate valve function, and detect coronary artery disease without invasive catheterization. Patients with chest pain could receive comprehensive cardiac evaluation through MRI, often avoiding more dangerous diagnostic procedures. Oncology was transformed as MRI enabled earlier cancer detection and more precise treatment planning. Breast MRI could identify cancers invisible to mammography. Prostate MRI improved the accuracy of cancer diagnosis and staging. Whole-body MRI screening programs were developed to detect metastatic disease throughout the body in single examinations. Pediatric medicine benefited enormously from MRI's radiation-free nature. Children could undergo comprehensive diagnostic imaging without radiation exposure concerns. Congenital abnormalities could be diagnosed prenatally using fetal MRI. Pediatric brain development could be studied longitudinally without cumulative radiation risks. Technological innovations continued expanding MRI's capabilities. Higher field strength magnets, operating at 3 Tesla and beyond, provided improved image resolution and faster scanning speeds. Real-time MRI enabled imaging of dynamic processes like swallowing, joint movement, and cardiac function. Molecular imaging techniques allowed visualization of cellular and biochemical processes within living tissues. Artificial intelligence integration began revolutionizing MRI interpretation and acquisition. Machine learning algorithms could detect subtle pathological changes that might be missed by human observers. Automated scan planning reduced examination times while maintaining diagnostic quality. Deep learning techniques enabled reconstruction of high-quality images from reduced datasets, further accelerating scan times. The economic impact was substantial. MRI examinations reduced the need for exploratory surgeries, invasive diagnostic procedures, and hospital admissions. Earlier disease detection often enabled less expensive treatments with better outcomes. The technology's ability to monitor treatment response allowed physicians to optimize therapy while minimizing side effects. Research applications expanded beyond clinical medicine. Pharmaceutical companies used MRI to evaluate drug effects in clinical trials. Sports medicine specialists studied injury mechanisms and healing processes. Evolutionary biologists examined brain structure across different species. The technology became an indispensable research tool across numerous scientific disciplines. Current MRI systems operate with capabilities that would have seemed impossible to the pioneers of the 1970s. Examinations that once required hours now complete in minutes. Image resolution rivals that of anatomical specimens. Multiparametric imaging provides quantitative measurements of tissue properties rather than just qualitative images. Looking toward the future, MRI continues evolving. Ultra-high field systems promise even greater resolution and sensitivity. Portable MRI systems could bring the technology to emergency departments and intensive care units. Molecular imaging may enable visualization of disease processes at the cellular level. The transformation from Bloch and Purcell's basic physics experiments to modern MRI represents one of science's greatest translation success stories. The journey from quantum mechanics to clinical medicine required visionary thinking, engineering, excellence, and collaborative effort across multiple disciplines. The result was a technology that gave humanity something it had never possessed: the ability to see inside living bodies without causing harm. Today, as MRI scanners operate around the clock in hospitals worldwide, generating images that guide medical decisions and save lives, they stand as monuments to human ingenuity and the power of scientific inquiry. The impossible became routine, the invisible became visible, and medicine was forever changed. The revolution realized continues to unfold, promising even greater insights into the mysteries of human biology and disease.